So, good afternoon, everyone. We start our first afternoon with Professor Gerhard Hempre from the Max Planck Institute of Quantum Optics from Garching, outskirts of Munich. Thank you for coming. Thank you for the time to come here and present. It's all yours.
Okay, first of all, thank you very much for the kind invitation. It's a great pleasure to be here. It's a long trip, 24 hours door to door or so. But it's always worthwhile to be here. So thanks also, thanks everyone who was involved in this meeting for inviting me here. It's really, really fun. So the topic is entanglement. We heard about entanglement already in the previous talk. The dark and bright states that we learned about from Celso are entangled states. So entanglement is at the heart of the double slit experiment in some sense. And I will tell you that entanglement is at the heart of many other things that I would like to talk to you and maybe briefly remind myself and maybe you that there is a history of entanglement. So I didn't actually know who is in the audience. So I really wanted to start a little bit from scratch, some historical remarks. It's 100 years of quantum physics. So I will make a few remarks which you might not know. Maybe you know, I don't know, let's see. You can tell me afterwards. And this is the untold story. And then I will proceed, so to say, to experiments that we did on entanglement which are not published. Not because they are not publishable, it's because they are so brand new that there is no paper yet on that. And there's a long tradition of transition, of course, from one regime into the other, which takes me an hour or so to explain. Okay, so entanglement. Of course, we all know that entanglement, as I said, is at the heart of quantum physics. It was invented, or the wording was coined by Schrödinger in 1935 and also by Einstein, which I will appreciate on the next slide. And he basically said the best possible, that's the definition of entanglement. The best possible knowledge of a whole does not include the best possible knowledge of its parts. And this is what keeps coming back to haunt us. And I think this is still true today. So there are many things about entanglement which are not yet explored, experimentally explored, maybe even theoretically explored. How to quantify entanglement in a multi-qubit system, for example, and I will talk about that. So that was 1935. Was a pretty positive statement in the context of Schrödinger's cat, of course. Now, Schrödinger's cat is also an entangled state between a cat being live or dead and the radioactive atom having decayed or not. So entanglement really started with Einstein in 1935. Schrödinger's cat paper, if you read the paper, it was kind of a little bit mysterious. Schrödinger didn't really know what to think about a cat being dead and alive at the same time. But Einstein really had a serious issue with entanglement. And I don't want to go into the details. I assume you know that part of the story. That was told by Einstein, namely that's the problem of non-locality in quantum physics that he addressed. So that was the first paper. Can quantum mechanical description of physical reality be considered complete? And Bohr immediately responded, as you might know, with a paper entitled, Can quantum mechanical description of physical reality be considered complete? So there are two papers with the same title but different authors. And of course, Bohr, in a very philosophical manner, tried to explain that quantum physics is correct, while Einstein was more on the side, quantum physics is not complete, there may be hidden variables and these things, and you know about that. So they had some discussion in 1935, and then many people picked up the topic and popularized the topic a little bit in the 1940s and 1950s. But there was no conclusion. There was no experiment that could, so to say, resolve the issue. So at some point in the 1950s, end of 1950s, early 1960s, all these discussions were considered philosophy of science, not hardcore science. It was just philosophy, interpretation. So that was the status, and you can read in many books about this philosophy of science aspect. But then came Bell. And Bell proposed an experimental test of this philosophy of science. So it was no longer philosophy, so it now came back to hardcore physics. He invented what's now called the Bell inequality, which is a classical inequality. And he was basically proposing to do an experiment and see whether this inequality can be violated. And the inequality is written on the blackboard there, and the experiment that he was thinking about is also shown on the blackboard. So basically you start with something which has spin 0, for example, and it decays into two particles, carries away angular momentum to the left, carries away angular momentum to the right. And then you measure this angular momentum in different bases, and then you can show quantum mechanically that this inequality, which you can read there, according to Einstein, would be less than 2, but quantum mechanics would allow any value between 2 and 2 times square root of 2. Okay? So this was Bell. It's a remarkable story because Bell was a technician in some sense. No? He was working at CERN, for example, and designing accelerators. But on Sundays, he said, on Sundays he has principles. So he was thinking about this, so to say, part-time in some sense. And this part-time is really, so to say, what we all remember from Bell. It's not the design of accelerators, which we remember. But the Bell inequality is something we remember. You have a question? Excuse me? This is a... Are you suggesting that I made up the photo? No. It's a real photo, which I found in the internet. Yeah, it's a real photo. Not with the text. The text is mine. No? And the text, but the text comes from some of the books where Bell contributed. Anyway, so this was in the early 60s, and that motivated John Clauser. Well, I'm keeping the story a little bit short to not overburden you with too many details. But John Clauser was the first one who realized, okay, maybe this inequality can be tested with an experiment. And this is the experiment that, actually this is the second generation of experiment that he designed and implemented and built and carried out at the University of Berkeley. This is a second quantum entanglement experiment. It's really a huge machine that was not so easy to operate and not so easy to build. And they just did it with 2 people. So it was just John Clauser and Friedman. Friedman and Clauser were then, so to say, the 2 authors of the paper. So there were just 2 people operating the system, which was quite a demanding thing. And by the way, both of them, of course, the PhD didn't have a permanent position, and also John Clauser didn't have a permanent position. So he was really investing his time, his energy, everything he had into this experiment. I come back to that in a few slides. So this was the experiment. And of course, he wasn't sure. I mean, to bet his own or her own life on something, you really want to make sure that this is a good bet. No? So for example, his father was a professor at Caltech, and Richard Feynman was a professor at Caltech as well. And his father organized a meeting between John Clauser and Feynman so that they can talk about, so to say, the experiment to be built up and test Bell inequalities. And Feynman basically kicked him out of his office, saying, well, when you have found an error in the experimental predictions of quantum theory, come back then and we can discuss your problem. Please remember, these were the heydays of quantum physics in some sense. Well, they're still heydays. But this was at a time when all the high energy physics found the new particles and so on. So this was really a fantastic time. Nobody was thinking about testing quantum physics in some sense, because this was considered philosophy of science. Anyway, but Clauser was not, so to say, threatened by being kicked out of Feynman's office. Clauser was a strong, or still is a strong person, and he went on with the experiment, and this is what he found. Friedman and Clauser, what the two found. So they were running the experiment, for example, this in the final version for 200 hours on a calcium isotope. The inequality, the Bell inequality in that particular case, was predicting something which is smaller than 1/4, 25%. And the quantum prediction was 30%, and what they observed was 30% with some error bar. So the conclusion of that experiment was Einstein was wrong, because they violated Bell inequality. So Einstein was wrong. Clear conclusion, and they published it in 1972. Clauser had some hope that with the success of this experiment, he could get a faculty position somewhere, tenure track or something. So he applied to Columbia again. He applied there before. Columbia told him, "We told you so. Now stop wasting money and go do some real physics." Sorry, and go do some real physics. Yeah. Very disappointing. Very disappointing. So he still didn't have a permanent position. He did this fantastic experiment. Of course, he got the Nobel Prize a few years ago, no? For exactly these experiments. But at that time, it was really hard to do it. And so the story, or what you can learn from that, is please go ahead with what your ideals are, what you want to do, and what you think is important, like John Clauser. It's a really good story. And it was not so trivial. There was a competing experiment at that time in Harvard by Holt and Pipkin. Holt was a PhD. Yeah, okay, we can discuss. It's a philosophical aspect that you bring here, and yes, you are right. You are right. And this is what I would like to communicate to you, in some sense, between the lines. No? So there was a competing experiment by Holt and Pipkin. Holt was a PhD. Pipkin was a supervisor at Harvard. They had mercury, so not calcium, mercury, running 155 hours, so comparable time. The inequality they were testing was the same one, less than 1/4. The prediction for their experiment was 26%, and what they saw was 21%. So their experiment clearly showed that Bohr was wrong, and Einstein was right. No? So it was complete contradiction to Clauser's experiment, and complete agreement with the classical interpretation in terms of Bell inequality. But apparently they didn't trust their own data, so that experiment remained unpublished. Of course, there's a PhD thesis, which you can maybe read if you want, but it's not published in some journal. I haven't talked to the people, but I guess they didn't trust their experiment. I mean, there was a competing experiment in 1972, which was in clear violation and confirmed quantum theory, but this one did not. And maybe they were afraid of going public with that result. So Holt graduated. That's a good story. But the paper was, there was no paper. Okay, anyway, so the status was then kind of summarized by Edwin Janes in the early 1970s, 1973 in this case. This will surely go down as one of the most incredible intellectual achievements in the history of science. Wow. They got the Nobel Prize, no? And of course there's more that I can tell you. There's Alain Aspect with his nice experiments. There's Anton Zeilinger with nice experiments. There are many experiments. I don't want to go into the details there and stop, so to say, the historical discussion here. But now we have to beat this statement here. And this is hard. Okay? So why should we go on if this incredible intellectual achievement has been made? Wow. I mean, we feel like very small. Anyway, so how could we possibly continue? And now this is my story, how I think we can continue, but you can maybe have a different opinion on that. My opinion is, if I look at the field of physics from a, let's say, larger perspective, there are two open questions in the context of entanglement. two questions or two topics in the context of quantum information science, which of course exploits the fact that there is entanglement. And one relates to quantum complexity and the other relates to quantum error correction. So for example, a multi-photon, I mean, we should not forget the Clauser experiment was just with two photons, no? One photon propagating to the left, one photon propagating to the right. So the question is, can we scale this up to more than two photons? 3, 4, 5, 6, 7, whatever. Is multi-photon entanglement useful? Can we really exploit it to invent or to come up with some technology which is not possible classically, which we need for quantum, where we need quantum physics and where we can really build a quantum technology on. And the other one, the quantum error correction, in some sense, is entanglement scalable, in particular the photonic entanglement. Is it scalable? Because for scalability, you probably need quantum error correction to make sure that the state, when it grows and becomes larger and larger and larger for many qubits, that the state is still entangled and has sufficiently high fidelity and so on. So I think this are at least two major topics in the field, as I would say. The first one, of course, includes quantum computation, quantum complexity. You exploit the quantum complexity to build a quantum computer, or do with a quantum computer things that you cannot do classically, and it requires quantum error correction, that's clear. So I think these are the two main topics these days, in my view, in quantum science. Do you agree? Do you have other proposals? Do you understand what I'm talking about? Too easy? Too slow? Fine? Perfect, good. So, let me show you, the rest of the talk will be devoted more or less to one topic. And this is the topic. Photons are nice qubits. You can do a lot with photons. For example, a double slit experiment. But the problem with photons is that they are lossy. They get lost. There's no conservation number for photons. Photons have a chemical potential equal to 0, and that means particle number is not conserved. So photons can get lost. It's a big issue. It's a big issue in particular in quantum communication. So basically what you do is, maybe this is Alice here, has a memory atom, and here's Bob, and they want to communicate via exchanging a qubit. And of course, if the distance is large, this will be a photonic qubit. So there are two possibilities. Either Alice maps her quantum state onto a photon, and the photon then propagates to Bob, is received by Bob and stored by Bob, let's say. Or alternatively, she can entangle, Alice can entangle with a flying photon. Photon goes to Bob, is stored there, and then you do a quantum teleportation experiment to communicate the information. So there are different possibilities, but both scenarios suffer from the fact that the photons are lost or can be lost, in particular when the distance becomes large. So if the distance is 10 kilometers or 20 or 100 or 1,000 or maybe around the Earth, then it's an issue. If I would like to communicate with Sérgio here in Brazil and I'm sitting in Munich, it's 10,000 kilometers or so, no photon will have a chance to survive. So this communication will not work. So we need repeaters, for example. We need quantum repeaters. But quantum repeaters are very, very hard to build. They're probably equally hard to build than quantum computers. They're hard. For reasons that I don't want to go into the details, but it's hard. So the alternative, a little bit the alternative, is to build what can be called a memoryless quantum repeater. So why should we, this is a question, why should we, for example, encode the information or the entanglement here with this photon? Why should we just encode it in one photon? Why not many? And then send many. So the alternative scenario is maybe this one. Okay? So we have the atom, and now we entangle the atom, which is a memory qubit. It doesn't need to be a real atom. It can be any spin. It can be anything. We entangle it with many photons. in this case here shown maybe 5 photons. And then 5 photons fly to Bob, and maybe some of them get lost. But if they're all entangled, we can hope to retrieve the information from the photons that arrive. At least if not too many photons are lost. Of course, if all photons are lost, then we are lost too. But maybe if the half of the photons are lost, then maybe we can retrieve information from the remaining photons that survive the propagation over the long distance. Okay, so the idea is to build an entangled state like this one, and then send the entangled state, and hope to be able to communicate more efficiently than would be possible with a single photon. That's the idea. Okay, and how to realize this idea? Well, first of all, we need to make this entangled state. We have to say we have so to say entangle a couple of photons with an atom. So how to do that? It's not so straightforward. Do we have a recipe? Do you know how to do this? Question to you? You can ask me also questions. Oh, sorry. Exactly. We are not cloning a qubit. So there's something like an entanglement monogamy. This maximum entanglement or maximum correlations can only appear between 2 qubits and not between, in this case, 6 qubits. So we are not encoding the same information in every photon because that would violate the no cloning principle. But we have to entangle this one atom, which is a sender, with a couple of photons and distribute the entanglement in such a way, hopefully, in such a way that if photons are lost, we can still retrieve the information. But there's a catch. I agree. Thank you for your question. Very good. Okay, so how do we do that? And here are the states which we are generating in the lab, and I tell you how to do this. They were kind of invented or brought into our physics community or quantum information community by Rausendorf and Briegel some 20 years ago. They're called graph states or cluster states sometimes. And there are different types of states that were proposed and that we can make. These are the ones that we can make in the lab, and I'll tell you how to do this. So there are linear cluster states like this one. There are star-shaped cluster states like this one. There are ring-shaped cluster states like this one, rectangular 4 qubits or 5 qubits or 6 qubits. So by the way, the open circles represent qubits, and the lines represent a gate which is done between the qubits. Okay, so you have a set of qubits, 1, 2, 3, 4, 5, whatever, and then you make gates between a selected number of qubits, and then you can generate this kind of state. Or what we also do, and this is something that I will address too, you can fuse 2, let's say star-like graph states like this one and this one, fuse them together to a state which is called a tree state, because it looks like a tree. It has a root qubit, it has branches, it has leaves, and so on. So you can really think about this as a new language to describe entanglement. But this is entanglement not in position space. No? We are not talking about a photon here or there or there. It's an entanglement in Hilbert space. The topology is in Hilbert space. No? So it's a little bit an abstract concept. So this is a little bit of formalism for the theorist among you. We need qubits with, let's say, a computational basis 0 and 1. We need single qubit rotations, so we have to prepare these qubits in a superposition state, 0 plus 1, for example, which I denote by plus. And equally, a 0 minus 1 would be denoted by minus, and so on. And then we need the gates. In this case, these are 2 qubit gates, which are of the form of a controlled Z, so a controlled phase gate, which is described in the computational basis as a diagonal matrix which has 3 entries being 1 and 1 entry being minus 1. So this is a 2 qubit gate. And then basically you prepare the overall state of all the qubits is outlined below. So you prepare all the qubits in a product state, all qubits being in plus here, all qubits plus in the product state, and then you connect along certain edges, which you can choose by this 2-qubit gate, and then it's just the product of all the 2-qubit gates acting on this product state, and that gives a graph state. That's what's called a graph state. So the recipe to make them is simple. To make them in the lab is more demanding, but the recipe conceptually is very simple. There's an alternative way. This emphasizes a little bit the production of the generation of the graph state. There's another view on graph state which emphasizes more the measurement. How can you prove that this is the graph state? And that is this one. It comes in the form of stabilizers. So probably some of you have heard about stabilizers, but maybe you are not all aware of what stabilizers are. So stabilizers are basically multi-qubit operators which were invented in the context of quantum error correction. And they make use of the Pauli operators, the X, the Y, and the Z. This is the standard Pauli operators. This describes here a bit flip. This describes a phase flip. And the Y operator is basically a product of X and Z. This is just a property of the Pauli operators. And now the stabilizers are defined in such a way that you take the product, the stabilizer on each qubit, A, and A runs from 1, 2, 3, 4, 5, 6, 7 over all the qubits. So it's measuring qubit A in the X basis and measuring all the qubits on the neighborhood of the qubit A in the Z basis. That's what's called a stabilizer. And this stabilizer, or the graph state, is an eigenvector or eigenstate to a stabilizer, to the stabilizer for all the A's with eigenvalue 1. So these two definitions that I gave you, the first definition in terms of gates and the second definition now here in terms of stabilizers, are mathematically completely equivalent. So you can switch back and forth between the two, no problem. But sometimes this one is more convenient to use and sometimes the other is more convenient to use. So let me explain this as an example. For example, this was the definition of the stabilizers. So let's assume you have something like this star state here. The stabilizer is just then for the middle one, for this one in the center, is just the X measuring this in X and this in Z and Z. And then you know the product of all of them is 1. So you don't have to measure the Z up here when you can measure the Z down there. And the nice thing is about the Z doesn't have to be measured, it can even be lost. So that's why it comes from quantum error correction. So we can, in principle, compensate losses. And that was a goal. You remember that that's the goal, to make an entangled state where we can retrieve information although photons are lost. Okay? So if this is lost here, it doesn't matter as long as, for example, these here are still available. So that's the idea. I can tell you hours and hours about graph states, but maybe one message is important, or one message is maybe what you should know. So let's assume we have a graph state which is a linear cluster state, in this case consisting of 5 qubits, and we are making maybe a measurement on the middle one in the X, Y, or Z basis. What is the result? Well, if I measure, for example, in the Z basis, I'm just projecting that qubit out because I'm doing a measurement on it, but I'm keeping the entanglement on the neighboring qubit intact. So the entanglement survives here and the entanglement survives there, but this qubit is just dropping out. So basically I'm cutting the long chain into pieces by making Z measurements. By making a Y measurement, like this one here, I'm actually dropping it out as well because I'm making a measurement, but at the same time I'm connecting this qubit with this one. Okay, so I'm taking one qubit out, but I'm reconnecting the other ones, which is a wonderful property. And similar for the X measurement. if I make an X measurement here, then this drops out, but this one here becomes entangled with this one, and the rest of the chain is entangled here. So in some sense, it produces a leaf. I have a long chain, I'm measuring one in the X basis, I'm producing a leaf. Okay, so there's a lot of, so to say, tricks one can play with the graph states, and that's what makes them so appealing. You can really do something with them. They're ideal tools. It's really fun to work with them because you can play with them. It's not just that entanglement is immediately dead, for example, when you make a measurement on one particle or so. No, it's not. You can do things with it. You can change the structure, for example, the topology of the cube of the entanglement with this kind of technique. And for example, let me just give you a straightforward example. Assume that we have a two-dimensional cluster state like this one here, and we want to project an entanglement between, let's say, this qubit and this qubit out of this reservoir, maybe far away. Maybe some of the qubits are lost. We have to find a way between this qubit and that qubit, a way where all the qubits survive. For example, this one here, we're making a y measurement along this line, and we're making z measurements in the surrounding qubits, and that isolates the entanglement between these two qubits and provides an entangled state which we can use, for example, for teleportation. So you can play with these things. And this is also very much related to measurement-based quantum computing, no? which makes use of similar techniques and similar ideas, basically. Okay. So basically what you should remember is maybe having a graph state as a resource, one can make an efficient entanglement routing based on an adaptive strategy. Depending on which qubit is lost or whatever, you can decide on a new strategy. What the best strategy is to achieve whatever you want to achieve is, so to say, an open topic. It's not so clear. I can't give you a recipe, so to say, what the optimum is, because it's an open research topic. So what the optimal resource is, for example, for one-way quantum repeater or one-way quantum computer is in the end not so clear. The hope is, and I'm a little bit sneaking into the future at the moment, the hope is basically that, for example, you can do something which Vanava and co-workers almost 20 years ago called counterfactual error correction. So you can design on a strategy and hope that maybe if the logical loss is plotted versus the physical loss of the qubits, of the photon, varying between, let's say, 0 and 1, and the logical loss, of course, also varying between 0 and 1. In that picture, the direct transmission of a photon would be a straight line here. But with this adaptive strategy, with having a resource state, a more complex graph state available as a resource, one could maybe hope that one comes into a regime where the logical loss is smaller than the physical loss. That would be fantastic. That would really be an example that entanglement is useful. It's really useful in the context of quantum communication. Anyway, so that's, so to say, the idea. So now let's come to the experiment. So what can we do in the lab? This is a picture from the lab. We have the graph state source is basically on this optical table. There's another optical table here which houses all the lasers. This optical table houses all the lasers, and then with optical fibers we bring them to the other table, and that's so to say where the graph states are produced. So how do we produce them? Basically, it's kind of simple conceptually again, but pretty demanding experimentally. It took us 15 years to do it. 15 years. We started in 2007, before your time. We started in 2007, and then finally we succeeded a few years ago, and I will tell you about it. So basically the idea is to have a cavity QED system with one atom placed between two high finesse optical mirrors. And then this system is, the atom is excited, it produces photons, the photons are entangled with the atom, and then a stream of photons, in principle, on a push of a button, a stream of photon comes out, they're all entangled with each other. The atom is a memory system. The atom has a nice property of being a memory, a quantum memory. So we can transfer, so to say, the coherence between photon, one photon and the next photon, via the long coherence time of the atom, make a stream of photons, and then at the end analyze how the properties of the photons look like, and from this conclude what kind of state we have actually generated. So maybe a few numbers from the first experiments that we had. The overall efficiency between the photon produced here on the push of a button and the click in the detector was roughly 43%, with an emission efficiency here in our source of around 65%, 2/3, the propagation 75%, detection 90%, or so the product is 43%, which is world record at that time. And we have improved in the meantime. I'll come back to that. Anyway, so this is the kind of system, and you can formally write it down in the following way. It's basically a concatenation of controlled atom photon gates. There's an atom here, and there are plenty of photons, 1, 2, 3, 4, 5, 6, 7. And then we make, as I said before, we make gates between the atom and the photon. Between the atom and the photon. And we concatenate that. And in between, we can make the Hadamard rotations on the atom, or maybe at the end, make Hadamard rotations on the photons. And this allows us, by designing the Hadamards, by designing which Hadamard is applied or not, we can engineer our entanglement topology in a certain way. For example, we can make linear cluster states with having the Hadamards up here. And we generated cluster states up to 12 photons, I will tell you about. And by having the Hadamards down here, we can generate these star or G8Z states with 14 photons. And then we stopped. We stopped at 14 photons because this was way more than what had been achieved before. So I could not convince the student to carry on with more photons. So this is in principle a straightforward strategy. As I said, experimentally it's not so easy, but it's a straightforward conceptual thing. And here are some results. How good can we do this? This is for the star states or the G8Z states. So where we plot, for example, the fidelity as a function of the photon number. The density matrix of a G8Z state is pretty easy. It's almost everywhere 0, except in the corners. If you plot the density matrix, then there are only 4 non-vanishing elements. It's this one here. This is a density matrix. Everything is 0 except basically the corners here. This one here and this one characterize the population, and this one here on the off diagonal characterize the coherence. And the fidelity is just the average of the population and the fidelity, according to this equation. Okay, so for photon numbers between 0 and 15 or so, our fidelity decays from, I don't know, 95% here to something like 14 photons is 80%. And if we trust this experiment and just extrapolate, I guess we can do 42 photons entangled in the G8Z state. And 42 is a nice number, as you know. It gives the answer to everything. You know that? You know the story? Hitchhiker's Guide to the Galaxy. 42 is the answer from Hitchhiker's Guide to the Galaxy. 42 is the... Well, somebody was asked some question, and the answer was always 42. Why 42? Because it's the answer to everything. Hitchhiker's Galaxy. If you have read it, then you can enjoy it. If you don't read it, okay, forget it. Anyway, so I think we could in principle make 42 entangled photons in a row, but it takes a little bit long time. So that's why we haven't done it. It's about 1% fidelity loss per photon. So it works remarkably well. So now I told you it stops. PowerPoint doesn't work anymore. Oops. I'm sorry. I'm sorry. Okay, as I said, we would like to, so to say, characterize our state. And for this, we have to measure the stabilizers. Here, this is basically trying to remember what stabilizers were. We measure basically 3 successive photons, or 3 neighboring photons. The middle one in the K basis. This is for a linear cluster state. The middle one in the X basis. This one here. And the neighboring ones in the Z basis. So these are the stabilizers, and this is the result. So they're all above 90%. So what does it mean? You're probably familiar with the concept of fidelity, but are you familiar with the concept of stabilizers? And is 90% now a high number or not? I mean, ideally it would be 100%, but now it's 90 plus percent. So is it good? So I didn't know, and asked Hans Briegel, for example, because he invented the whole thing, and I asked him, some years ago, can you explain to me what stabilizers really mean? Is 90% high or low? And he said, basically, said, okay, our stabilizers are a good way to characterize a state. Can you explain to me what fidelity means? And so we were off by 180 degrees. No? I believed that I knew what a fidelity is, and he said he doesn't understand fidelity. And I didn't know stabilizer, and he knew stabilizers very well. And he said it's very, very, so to say, straightforward. You look at the local correlations. No? There's a larger state, and you look at the local correlation. How good is a local correlation without taking into account all the qubits which are far away? And that's what this equation basically says. So having a correlation above 90% means the error is less than 10%. So it's pretty straightforward to understand. But nevertheless, I was wondering, can we characterize the fidelity of the state as a whole, with these 10 or dozen or whatever number of photons? Can we understand the fidelity as a whole? And there's no simple relationship between stabilizers and fidelity. There's a lower bound, and we also developed an upper bound for the fidelity of the whole state, and this is plotted here. So basically, a lower bound has been proposed some years ago by Thors and Güne, and it's this equation here, basically. So you take a product of all the even stabilizers, and you add the product of all the odd stabilizers, well, +1 divided by 2, -1, and then takes the expectation value, and that gives a lower bound. So this is a lower bound of the fidelity of the whole state here. Okay, So for 12 photons, the lower bound says we are above 50%, so it's non-classical. The upper bound that we derived, and I don't want to go into the details here, says something more like 80%. So the fidelity is somewhere between the two regions here, so clearly in the quantum domain. The whole state with all these qubits, not the local correlation, but the global correlation. So that's what the fidelity tells us. Good. So how does the system work? This actually plots the coincidence rate, how many entangled states we can make in the lab as a function of the photon number, which is plotted on the horizontal axis. With all the existing experiments at that time, and that time was 3 years ago, 2022, and for us, we plot the G8Z states and the cluster states up to a dozen or 14 photons, and this is a line that we observe. So we make, for example, a G8Z state with a dozen photons, or maybe even 14 photons, once a minute, or maybe every 2 minutes, one state, which is orders of magnitude higher than if you compare it with SPDC sources, for example, spontaneous parametric downconversion sources. The previous record was 1 for 12 photons, 1 every hour. Or with 14 photons, they couldn't do it because it would give less than 1 state per day. So it's a pretty efficient system. So we were quite happy with that. So now I told you we need to make the rings or the trees or so. And to do that, we need a new technology, which I would like to briefly mention. It's what we call graph state fusion. So we now take conceptually 2 cluster states, 2 G8Z states. For example, this is one, and that's another one, emitted now by 2 atoms in the cavity. And then we do, let's say this is the atomic qubit, then we do a Bell state measurement on these 2 atomic qubits, and in this way entangle the 2 in the cavity, and that makes a tree state. A tree state where the root qubit has 2 physical qubits in it. So 1 logical qubit, but 2 physical qubits. Okay. So that allows us to make a tree state, for example. This shows a little bit of how this graph state fusion works. I don't want to go into the details here. This is the protocol. I don't walk you through the details of it. I just would like to say, well, we have these 2 atoms here, atom number 1, atom number 2. We are producing these photons here, effectively making these gates, entangling the atoms and the photons in parallel. And then we're making 2 independent entangled states. No? So this is atom-photon entanglement from one of the atoms. This is the other atom. We are building these star states, and then we're making the fusion and arrive at what we call the tree state, which we then verified in the end by reading out the system. So the protocol is a little bit, let's say, complex, but works pretty well. So here's the result. So these are the 2-dimensional tree states that we make. Again, to remind you, this is a tree here. This is a tree. This is a fusion. This is a result of the fusion here. So 2 physical qubits and 1 logical qubit as a root qubit. And these are the 2 branches, and these are the 4 leaves. So in total, we have 4, 5, 6, 7 logical qubits and 8 physical qubits. So if you would write down the state, the tree state that we make, then it's this state down here. The state down here has 128 terms, 7 qubits, each in up or down, or superposition. If you write down the state, this has 128 terms. These are the 128 terms. And it's not very visible. The entanglement topology is not very visible. And that's why we do like this language here, namely that we characterize a state by this picture here. And again, these are the stabilizers. So we measure the stabilizers and they're all 90% or so. There's some variation here, but they're kind of 90% value. So we can nicely make the tree states. I told you about the ring states. Here's an example for the ring states, actually two examples. A 4 logical qubit ring and a 6 logical qubit ring, which is this one, for which we have to make the fusion twice. So the general idea is to make 2 linear cluster states from one atom, one, and another one from the other atom, and then fuse both ends together. That makes a ring. You have to believe me. and this is what the stabilizers basically tell us. So we are pretty good in making a 4 qubit ring. We were not so good, let's say, in making a 6 qubit ring. It has somewhat smaller stabilizers, but still it's kind of a good ring, good entanglement ring. So now, what to do with them? And I have 10 minutes, or how much? When we start a little bit later. Okay, so now the question is, does this help us? I'm coming back to the questions that are raised at the beginning. Does this help us to communicate more efficiently than with just a single qubit? That was, so to say, the thing that I started at the beginning, and that was, so to say, the question. And the question is, can we address this issue, and how far can we go, and where are we, and so on. And this is something I would like to tell you now. Okay, please remember, we're making this ring. One part of the ring is an atomic qubit, stationary, and the other are photons, and the photons are flying from, let's say, Alice to Bob. You can give it any name, doesn't matter. But they're flying. So now this number 6 here is something which is our atom, let's say. And these here, 1, 2, 3, 4, 5, are the photonic qubits. This is a ring, no? The simple version of the ring, only pointing out the logical qubit, not the physical qubit, because this is fused together, so some of the qubits are actually 2 qubits, but 1 logical qubit. And this points out only the logical qubits. So now assume that this ring is flying, apart from the 6, because the 6 is the atom, which is stationary, and the photons are flying away. 1, 2, 3, 4, 5. And let's assume that photon number 1 and photon number 3 and photon number 5 are lost. Just as an example. Okay? So this one is maybe lost, this one is lost, and this one is lost. Can we retrieve from the remaining ones, that is 2 and 4, can we retrieve the information, so to say, that we encoded in the ring with the qubit number 6, which is Alice qubit? And this is very simple in this case. We just have to measure the stabilizer as 4. By definition, it's 1, or ideally it's 1. But this stabilizer is just the product of Pauli operators, Z, X, Z. The first Z measured on X, and then X, qubit number 4 we measure in X, and qubit number 2 we measure in Z. Okay, so it's plotted here again. So we measure number 4, qubit number 4 in X, and number 2 in Z, and that carries the information that was encoded in the ring. In this example, so that's a straightforward example. But even 3 qubits can be lost and we can retrieve the information, which is good news. So let's look at a little bit more complicated situation. Let's assume as another example, and there are many, many examples which I could walk you through. But this is a little bit more complicated example where maybe qubit number 1 is lost, and qubit number 4 and qubit number 5. Can we retrieve this correlation again? Even in this case, 3 qubits are lost. Can we retrieve the information? And the answer is yes. And it's shown down here. So let's look at stabilizer S6. It's a stabilizer around qubit number 6, with a neighborhood being 4 and 5. Okay? So the product x6 times z4 times z5 is 1 by definition. But 4 and 5 are missing, they're lost. But 4 and 5 can be retrieved by looking at the stabilizers here, 4, 2, and 1 on the one hand, and 5, 3, and 1 on the other hand. So we just insert, let's say here z4 times z4. The x on qubit number 6 stays as it is. Z4 was there already. So we insert z4 times x2 times z1, which is, so to say, the stabilizer on this side here. And then comes a stabilizer on the other side, 5, 3, and 1. This is 5, 3, and 1. Now we're making use of the fact that the measurement in each basis can either be +1 or -1 as a result. The qubit you measure in a certain direction is up or down, 1 or -1. So the product of 1 times 1 is 1, and -1 times -1 is 1. Okay, so the product of the z's here is 1. This is 1. The product of the z's here is 1. The product of the z's is 1. So we arrive at this here. Okay, so this is pointer disappears. So this here is 1, and it's the same as this one. So we're making a measurement on qubit 6 and x2, qubit 2 and 3, both in the x spaces. Maybe we can retrieve the information. And there are way more examples and way more scenarios and way more cases where only maybe all qubits arrive and maybe only 1 qubit is lost and maybe only 2 qubits are lost. These are 2 examples where 3 qubits are lost. Maybe 4 qubits are lost. Maybe 5 qubits are lost. And so if you write it down basically and summarize over all the possibilities, which comes on the next slide, then you can write it down in terms of the loss. So please remember we were talking about physical loss and the logical loss. So as a physical loss, I define as the average number of failures, that means photon not detected, it's lost, per photon generation attempt. So it's 1 minus the efficiency. The loss is 1 minus the efficiency. And the logical loss is very similar. The logical loss defined as 1 minus the logical efficiency. It's the average number of failures per graph state generation. So in some sense, this is just the transmission with a single qubit, and this is the transmission with the graph state. And this is what comes out. So if you add over the different cases, remember 1 qubit could be lost, 0 qubit could be lost, or 2 or 3, whatever. You come up with a logical efficiency for an X or Y or Z measurement versus the physical efficiency is given by this equation. It's just basically straightforward. The first case means there's no photon lost. This case here, there's no photon lost. There's 1 photon lost. There are 2 photons lost. There are 3 photons lost. And if there are 4 or 5 photons lost, I cannot retrieve any information. I can also ask myself what happens if I'm interested not only in an X or Z measurement, but in both, measuring both X and Z. Then I call this not the logical efficiency, but the entanglement efficiency. And that has a slightly different form, where 1 and 2 photons are lost. Because in all the cases up here, I cannot retrieve X and Z, but I can retrieve only X or Z. Anyway, these are the 2 cases that I can consider. And if I plot this equation that I just showed you, it's this one. So plotted is a logical loss as a physical loss, as a function of the physical loss, varying between 0 and 1. So here everything is lost, and here nothing is lost. And logical loss, everything is lost. Sorry, everything survives, and everything is lost. The dashed line is just the 1 photon reference line, where the logical loss is equal to the physical loss. But for the graph state, it shows, for this 6-qubit ring state, for the particular case of the 6-qubit ring state, it's basically a curve like this one, which has this S shape. And the nice thing is the logical loss can be smaller than the physical loss once the physical loss is lower than 50%. This is what we were, so to say, looking for. But this is theory. No? So let's do the experiment. The experiment is hard because we have to beat the 50%. Push a button, generate a photon, propagate it through our system, detect it. And this with an efficiency of better than 50%. For each photon, this turned out to be a real challenge. So the student worked on it for about a year or so. He looked at every mirror, every beam splitter, every fiber coupler, every whatever, tried to improve it. And every fraction of a percent counts in the end. So here's basically a list of things where we plot the efficiency for the different optical components. The lenses, doublets, mirrors, filters, wave plates, EOMs, polarizing beam splitters, blah, 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 fiber lengths, whatever. And you can see the efficiencies are all kind of 99%, higher than 99%, except maybe for the detector efficiency, which is only 95%. So we couldn't make it better than 95%, which is already quite good. Well, in principle, we could make it a little bit better, but then the detector shows more noise. So in the end, what counts is signal to noise. In physics, it's always signal to noise that counts. Anyway, so we were happy that the overall efficiency in the end was 52%, including emission. Emission is not on the table here. So the bottleneck is the production of the photon by the atom in the cavity and coupling it out of the vacuum system, which is 2/3. So the total efficiency in the end was 52%. And these are the data then. So it's the same graph that I showed you before. Same graph, but now it contains experimental data. And the data start maybe up here with high losses. I mean, having a lossy system is easy. High losses, and then the losses go down, go down, go down. And we were wondering, can we cross this threshold here and enter this new regime of being below 50%? And yes, we can enter it. We could go down to 48% losses, which means 52% efficiency. And it's clear that they are below the straight line. Okay? So for the first time ever, we could see, so to say, that the logical losses are smaller than the physical losses, or the logical efficiency is higher than the physical efficiency. So entanglement works. Entanglement is good. It's just marginal, a few percent, but it's there. It's there, and that's basically the message. Okay, so maybe what's that? In the interest of time, maybe I skip this here, where we do the entanglement and measure the fidelity and so on, 71%, with error correction 75%. I switched this one. I just would like to sort of say, maybe briefly mention a possibility how to improve the efficiency beyond the 52%. As you can see from the losses of the mirrors and the beam splitters and so on, it's maybe not so easily possible. The bottleneck is a cavity QED system with the 2/3. So how can we improve the 2/3? 2/3 means that 1/3 are losses. And with that in mind, we did an experiment on multiplexing. So we generated an ensemble of atoms in a cavity. This is a cavity here. And we have an array of atoms implemented with optical tweezers. It could be a 2x2 matrix here, or a 2-dimensional array. It could also be a 1-dimensional array. And this is 1, 2, 3, 4, 5, 6, 7 atoms in a cavity, individually addressable. We can entangle each of them with a photon. and see, so to say, how well that works. This picture here basically shows the probability, the success probability of building such a register with more than one atom. And with the tweezers, we arrive at probabilities of the order of, let's say, 10% or maybe even several 10%, while the probabilistic loading that we were using in the past, I didn't mention that really, the probabilistic loading gives us an efficiency which is extremely small. But with optical tweezers, we can really arrange a set of atoms in the cavity and keep it there and entangle them. And this is a result of the entanglement. So this is a case for 1, 2, 3, 4, 5, 6 atoms here. 1, 2, 3, 4, 5, 6, 7 atoms. And this is the efficiency of how well we can generate atom-photon entanglement as a function of atom number. And we reach almost 100%, 99% or so. So now we have a source where we have not a single atom, but many atoms, but with a high efficiency. And one of the future ideas would be, so to say, to entangle this, the 6 or 7 atoms that we have to form, let's say, one logical qubit. Very much in the spirit of the ring states or the tree state, where we have several or 2 physical qubits as one logical qubit. So here it would be maybe 6 or 7 atoms as one logical qubit, but having an emission probability and entanglement efficiency of close to 100%. And this is what this plot shows. So in some sense, we are optimistic that we are not limited by the 52%, by the small effect that we see, but we can in the future make have a higher efficiency, and in this way, so to say, enter deeper into the regime where quantum physics and the entanglement physics really pays off. Okay, with that, let me summarize. Basically, I posed, so to say, 2 questions or two comments at the beginning. What are the big issues in quantum science at the moment? Quantum complexity and quantum error correction. And I think what we have shown, or our contribution to this, is that with our system we can make arbitrary entanglement topologies, almost arbitrary, individual. They can be created at will, and even small scale entanglement topologies, like a 6-qubit ring. It's not so big. No? A 6-qubit ring is already useful in beating classical physics. That's wonderful. Okay, that's the end. Here's our entanglement zoo that we made so far. Linear cluster states with 12 photons, star state with 14 photons, and then these rings with 4 qubits and 5 qubits and 6 qubits and the trees. And the people involved, and this is most important, is Olivier Morin as a wonderful postdoc, Leonardo Russo, a PhD student, and Philippe Thomas just graduated a couple of months ago. And part of this work was done in collaboration with the groups of Anders Sørensen at the Niels Bohr Institute in Denmark and Stefano Persani as another PI in Denmark, and Love Pettersen as a PhD student in Denmark. It's a wonderful collaboration. Without them, we would not be, so to say, we would have had a harder time with the entanglement. Thank you very much.
Thank you, Gerhard. Questions?
Gerhard, about the photon, the state of the photon is encoded in the polarization or time being?
Polarization. The qubits are all, the photonic polarization qubits are, the photonic qubits are polarization qubits, and the atom is a spin qubit.
Okay, but you didn't mention, but you were telling me that you are planning to do the quantum memory 20 kilometers far away each other.
No, this is not 20 kilometers.
No, I know, but to do that...
This is 30 meters.
Okay, but to do that, you need a optical fiber connecting the labs, right?
It's an optical fiber, yeah.
Then in this case, the polarization is not maintained during the propagation, right? So I mean, if
Oh,
you
no,
would,
no,
if you
the,
use
the fiber is perfect in keeping the polarization. There's no depolarization in the fiber.
in your case, but in how can I say in the fiber installed in the city, you have not so good fibers, right? So
No, we have very good fibers. And the best fibers actually that we can have is a fiber that runs between cities. It's better than the fiber in the lab.
really, and
I was I,
polarization maintaining.
I was actually surprised to see this. And why is that? Well, the fiber that runs, we have another experiment that Celso is referring to, and which I didn't talk about. We have a connection experiment between two different cities. In each city, there's one atom. And it's 20 kilometer or 24 kilometer of optical fiber. And this fiber is extremely stable in polarization. Why? Because it's underground. The perfect temperature stabilization. We have to align the polarization or recalibrate the polarization every couple of hours or so, and it drifts by maybe a degree or a few degrees or so. It's way more stable than in the lab. Because in the lab, we go out of the lab and we go into another lab, and there's a building and temperature changes and the sun comes in and all these bad things are happening. But in the long fiber, it's very stable. So I love polarization qubits. They're much easier to use than, let's say, time bin qubits. Much easier because it's just a wave plate which rotates the polarization. It's very simple and it's very stable. And it's a diploid fiber that we have. This long fiber is a diploid fiber which was there already years ago, and we are yet just using it. Perfect.
Another question.
Thank you, Professor, for your kind and a nice talk. Can you put the previous slide, please?
Which slide?
The previous one.
This
slide.
one?
Transparency, yes. No, the previous one.
The previous one. Oh, sorry.
Just a doubt, because you said that even a few qubits is enough to, for example, surpass.
You mean this one or which one?
No, but I can tell you, because you said that a few qubits can beat classical physics. I wonder what kind of task it's when you said that the topology you said that this is enough to beat classical physics. In a certain slide you said this.
I'm not sure if I understand the question. You're asking which topology is best, or which topology does what?
Yeah, because the entanglement for in a few qubits is enough to beat classical operations. I mean, I don't know. I guess is the maybe one or two slides before this last one. Okay. Sorry, Professor.
So you tell me when to stop?
Mm-hmm. Ooh, not less than. Okay.
I'm going back.
Okay, no. Okay, no problem. I am a little lost here, but I mean, you affirm that a few qubits in this topology, no matter the kind of topology, it's enough to beat, for example, classical tasks. Is that correct?
Yeah, exactly. Okay. So the beautiful thing. So why is the ring so beautiful? Maybe I didn't mention or explain. I apologize. For the ring, the nice thing is if you lose particles on the left side, you reconstruct the stabilizers on the right side, and vice versa.
Yeah.
So you have different possibilities. So that's nice about the rings. Very intuitively in some sense.
Okay.
Now you could ask the question: how many qubits do I need in the ring? Why 6? Why not 7? Why not 5?
Okay.
And magically, and I have no explanation for that, magically it turns out that 6 is the best.
Nice, nice.
5 is not as good as 6, and 7 is not as good as 6.
Okay.
But I don't have an answer to why that is the case. So 6 is something magic.
Okay, thank you.
In entanglement terms, no? So it comes out of the math. No? The math that I've tried to explain to you with these examples, you can do for 5 qubits in a ring, or 6 qubits, or 7 qubits, and it turns out that 6 is, so to say, the best. Given, of course, our capabilities to generate these rings. So maybe 20 qubits are even better, I don't know. But 20 qubits in a ring we can't make.
Further questions?
So basically what I try to say is the best resources for these kind of experiments is not known. So people are investigating this. No? And as I also said, the tree states are also nice, and tree states have actually been proposed to do these kind of experiments too, but you would need, in order to beat this classical limit for the tree states, you would need another layer of leaves, or another branch, no? more leaves, more levels, no? If you like. And it's hard experimentally.
I don't see further questions, so let's thank Professor Gerhard again. We have a short break and we come back in half an hour. Okay, thank you. This is the last talk today from Daniel Magalhães from our institute. And although he is talking about timekeeping, we're a bit late. And just a reminder, we restart tomorrow at 9. Okay, be here, please. Daniel, thank you very much.
Thank you. Hey, nice to be here. Thank you for the invitation. And Emmanuel said already the first joke. That is we are going to talk about atomic clocks, and we are already late. And the second one, if I pass the time, and then that's because I work with atomic clocks. I bring some slides here just to have a brief discussion, maybe some not historical aspects, but maybe some timing evolution of these techniques used for atomic frequency standards. That's more technical name used for this kind of systems. And then the first thing I have to say to you that we are maybe not so much talk about atomic clocks, because a clock is a time base that is accumulated, and then with this accumulation we have time stamps, and then we have a complete clock. So a complete clock is a time base that's represented by the pendulum here, and then a counter that accumulates these periodic events. It's like, because only the frequency you have all the redundancy, and then it's like you count days, but you have to know what is the day of the year you are. Kind of. This is just a tough comparison. And a clock, and an atomic standards, that is what we are going to talk about. It's much more frequency base that is based on an atomic transition. So I am representing here this atomic transition that is the actual definition of the second. This is the hyperfine state of the transition of the fundamental state of cesium. So it's in the microwave domain. It's about 9 gigahertz. And it's for the neutral cesium state, okay? And this is come from the 60s. The definition comes from the 60s. That's the formal definition of the second as a primary unit. And I am going to talk a bit more about this definition at the end of the talk, okay? This is based on the magnetic resonance method that was already told by in the video of Dan Kleppner in the very beginning. And it was amazing that he already introduced this, that we can excite the atom and provide what we call an interrogation of the atomic transition. And once the atom passes in a microwave region, we can see the evolution of the probability between the two states of this atom. And then we say that if we are in the right frequency, we can see a peak of resonance. And then we know that the atom is experimenting the right frequency that we want to have as a reference. So this is hopefully how is done the kind of experiment. This is the very simple experiment did first by Rabi, and then afterwards we can think on this as an atomic reference, saying that we can interrogate the atomic system or the atoms, and then see if we see a resonance and feedback to a microwave synthesizer. We call it a local oscillator or macroscopic oscillator. This is just to, I would say, demystify that we have an atom that is oscillating in 9 gigahertz. It's not oscillating 9 gigahertz. If we provide the right frequency, it just oscillates half of a frequency, in fact, half of a period, in fact. So it's just the probe, the atom is a passive reference that responds to an excitation of 9 gigahertz in the case of cesium, okay? And after a while, we had what I call it here, the Ramsey's insight. Is that what we had here is that this transition could be thinner and thinner depending on the time of the interrogation. The time that the atom passes under the interaction of the microwave field. If the atom passes much more time, you can observe thinner resonance. But it was not technically feasible for longer times, to obtain longer times, because you have to have only a half of oscillation, and then you have to decrease the microwave field to so low values that it goes to just noise, in fact. And then instead of just decreasing or increasing the region, the interrogation region, and then decreasing the amplitude of the field, what Ramsey proposed, and this gave place to the Nobel Prize, as Kleppner said, the late Nobel Prize, is that he separated the fields, so he must not, he should not decrease the amplitude of the field to so low values. He could maintain in higher values, but he could spread or take longer the interrogation time. This was the insight that he had by that time. So keeping the superposition of states in the middle, in the blank region. Nowadays, this is one of the gates of the logic gates used for quantum computing too. But this is called the Ramsey separated field methods. And he tested also with a lot of variations, and these are the simulations that he had by that time. This is from the Nobel paper, the Nobel lecture paper from Ramsey. But he started doing with 2 oscillatory fields, and then you observe a good resonance. He started to apply 3 oscillatory fields and much more oscillatory fields, but it was observed that it was going even to have it thicker, the resonance, not improving so much the resonance. And this is interesting because he said in the Nobel lecture that the good step was passing to a single interrogation field to 2, but not just increasing so much. Nowadays in magnetic resonance, people use a lot of sequence of pulse, but just to have spin echoes and such kind of effects to separate from noise and such kind of things. But this is not from the pure Ramsey method to improve and to get the resonance really thinner in the sense of improving the method, okay? And so what he did, if we take a look in the same, I kept in this simulation here, I kept the same time for the same length of the interrogation field here, the interrogation region here, and then if we have 2 regions here, but separated by 10 times the length of the microwave region, we can improve the central resonance much more than the larger one that is kept here. And this is interesting because this is interpreted as the larger one is the probability that the transition had occurred in one of the regions here and not in the other one, or in this other one and not in this one. And the interference here, the oscillatory part here, that's the Ramsey fringe, is the probability that the transition occurs during the whole interrogation region. That's 2 microwave pulses and a steady or a blank region, but keeping the superposition of states, okay? In fact, we have a partial evolution of the state of the probability here. It maintains in a superposition of state. This is a particular case that you have 50-50 probability, and then you continue to evolve in the second region, okay? But this gives, the most important part here is that we have a very thinner resonance in the center. So this is equivalent of having the central part only. Is roughly equivalent of having a single pulse with a very long or 2 small L's and a capital L of length and in the overall. And this was the outstanding achievement that Ramsey bring to this method, and not only technically, but with the physics of superposition of states in the middle. One of the things, and probably one of the things here that prevented of improving too, of having more oscillatory fields, is that this is the ideal case, okay? I am comparing the response of this method with a single velocity, with a single atom, and this I'm calling as a probability function here. But once you have, and by the 30s, 40s, and 50s, we had, until the 80s, we had only thermal jets of atoms. We had, in fact, a source of atoms with a long or a very spread of velocities in the distribution of these atoms. And then what we had is the integration, let's say, or the weighted combination of response for each velocity class here, each one of them giving a different length or different time of interrogation. And so when you have at the end is the integration of all them, or the addition of all them. And then you have sometimes not all the oscillations that you could have for a single velocity as here, because you have destructive and constructive contributions, and then only in the central resonance you have the the main peak, but then you can enlarge it or not depending on the velocity distribution that you have in your source of atoms. And only by the end of the 80s, and of course, if people try to improve the system, getting the resonance thinner by increasing the length of the interrogation region, this was tried by, I think, the middle of 50s, in an experiment of at MIT, I think, that was called the Zacharias fountain, because they tried to launch a thermal beam of atoms and to see how they could increase the interrogation time when the atoms they fall down by gravity. But of course, they didn't see any atom, any single atom falling back by that time, even calculating all the length that they could have with the velocity distribution that they could observe. But it was not feasible experiment. They tried a lot, but it was not feasible. And only by the end of the 80s, with the advent of cold atoms, then they came back. They had a revival of the idea of Zacharias, and then they have again a source, but now with a source of cold atoms. And then you could have this idea of an atomic fountain again, but with a sample of cold atoms accelerated upwards and falling down by gravity in seconds, and you could have the same experiment by the beginning of the 90s, and then you could observe hopefully the fringe, the Ramsey fringe, as the ideal case of a single velocity of a system. This is a result that we had here in our lab, but this is all the interference, the experimental interference that we could observe, and you see that's comparable with the single velocity. And it's almost monocinetic. The destructive interference you could observe here, that's not perfectly touching the zero when you have some detuning in the central frequency of the clock transition here. Okay, but it's interesting because if you see these kind of, sorry, I have to return here a bit, but if you could see these in commercial clocks or thermal clocks, you could have a kind of 1 kilohertz of line width observed in the resonance, and with cold atoms, we can observe hopefully hertz of line width. This is less than 2 hertz of line width, and in higher fountains, higher launchings, you can observe even less than 1 hertz. When to have an atomic reference, we have to take into account not only the resonance, but then we have to see how to maintain the interrogation, because this is a bit more technical, let's say. This is more operational. When having a clock, you don't want it, and people that have this kind of experiment, very rarely they measure the whole fringe. This takes kind of some hours to take the whole fringe, because each launching takes some seconds, and then so to have kind of 1,000 points, then you have more than 1 hour for a single measurement. And for a clock, this is not feasible. So what we do is to have only 2 sides of the fringe here. So you measure in the half of the height here, and you compare the two values to see if you are going out of resonance or not, just a kind of differential measurement in the sides of the fringe, okay? But then you have the central transition, let's say, and then you say, oh, I am referenced to an atomic transition. Yes, you are referenced to atomic transition. Depending on the signal to noise you have, and depending on the stability of you have, and the quality of you have, that you have from your macroscopic oscillator, your microwave source, for example, and then you have a lot of precision and stability. This is the first nomenclature that I like to emphasize here. So you can have all the precision and to measure almost every time the same value, but not necessarily the right value. So this makes much more sense to talk about accuracy, and it's the fact that you have to take into account all the systematic effects that you can have, because your atomic transition can be shifted a little bit by magnetic field, by redshift deviation, by black body radiation interference, and a lot of things that shifts and add an offset of in the atomic transition. So to have accuracy, you have to take into account all these effects, and so that's why you have two kinds of analysis. I'm stressing this because when we are going to see some results, some very recent results, we will see this difference here. Sometimes they talk about stability, sometimes they talk about inaccuracy. So it's because to talk about accuracy, it's a little bit tricky. Okay, but then we have to take into account these the statistics uncertainties only, the randomness, and so this is more about precision, and type B because of systematic effects that you can have. So these carry uncertainties like temperature of the environment, altitude that your environment is, and so on. And so these carry on all the uncertainties that you can have, and you have to evaluate against accuracy. In fact, you can have some standards, some reference with less stability, but the difference is that you have to measure more to have more accuracy. So you have to converge to a central value, then you have to measure more. This is how we can say here. So these are the effects that you can take into account. The list is much longer than this. Like you have to take into account atomic collisions, and if you have microwave leakage in this sense, this depends on the transition you are observing. They are sensitive to environmental effects, and so it can change a bit these main factors here. Another point that we take into account, it's much about stability, and the evaluation is always told in terms of a strange standard deviation that's called the Allen variance or Allen standard deviation. And sometimes people are a bit in a trap when looking on these kind of results here. So what is 1 × 10⁻13 tau to minus 1.5? It means that if you have 1 by 1 second of measurements, you have the uncertainty of 10 to minus 13. If you integrate more, you go down with the number of samples by the square root of 2. This is the most common for normal distribution. If you have the just white noise, you go down with the number of measurements by the square root of the number of measurements. But this is only one of the effects that you can have here, or one of the behaviors that you can observe in this kind of measurements. And there can be others here. This is somehow the representation of the white noise, but you can have this kind of effect if you have other seasonal effects, for example, like day to night difference, like a cable that is changing with temperature and then take longer, and so on. And so you have to take this into account when you are evaluating. For example, if we have here a set of measurements, these are comparisons of remote clocks, and we can see that there is one that is very bad. There is the green one that's very good here. And then I can say maybe the blue one is smoother than the amber one here, okay? But when I evaluate just in the first glance, if I evaluate only the standard deviation, they could be comparable, and I could say even that the blue one is better than the orange one here. But if I take a look in this kind of analysis here, what I see is in short periods here, the orange one is not so good in terms of stability, and the blue one is better because it's smoothed. But if I take longer average, the blue one, it's not improving. So if I want to take more and more measurements to improve my result, to converge to a central value, what I see is that the noise that's present in the blue measurements here is not converging very well. It will only start to converge after a while. This is in days, in fact, in seconds. So this is hopefully 1 day here. So this is slightly more than half a day. And then the orange one is converging, and they go to the same results after half of a day of measurement. So, I mean, just to analyzing these two systems here, these two kinds of results here, that appears to be one much better than the other, and at the end of the day, they are comparable if you go to the same kind of analysis after a while, okay? And this is to call your attention that it's not necessary to have only the 10 to minus higher number to have the best system that you can have good results. All these systems here, all these reference here that we can use for these such kind of clocks here, we have already in daily use for timekeeping applications. Some of them, just to cite some of them, we have the use for frequency reference in higher communication rates. In more reliable systems, we have linked the power supply systems for cities, for the country, for example. Everything is synchronized because you have to have parallel source of supplies, and then you have all them synchronized by timing or frequency reference. And even timestamp for money transactions for dollar exchange, for example, they are validated by timing reference. So this makes us very, I would say, very dependable of all this frequency and time reference. Some of them just require frequency reference, like power supplies, just frequency that's enough to have the reference. But for money transactions, for example, you need the frequency, the oscillations accumulated, and then you have an absolute scale for validation of money exchange or such kind of things. Another application of timing is for the geolocation that we call geolocalization, and it's based on the time stamp evaluated the difference of a different source of these stamps, and then you evaluate the arrival time of each of them in a single receiver, and then you locate, and a better location you have, better the clock you have in the satellites, in the remote reference, and in the local comparator that you are taking the reference also. So like 1 nanosecond, hopefully some centimeters already of location of uncertainty in location that you can find. And this is much more disturbed nowadays, not because of the source of frequency, but much more about the path that you can see in the signal that's passing by a troposphere, a ionosphere. So you have to have better models to characterize these paths. And another very interesting let's say, another very interesting thing that happened, it was the redefinition of the international system of units, and this was much more because of the more reliable measurements that we had, and more spectroscopy measurements like voltage and resistance standards that we had, and much more based in frequency reference. And then we had in 2019 the redefinition of the international system of units, and nowadays is under discussion the redefinition of the second, that's based in the microwave transition of the cesium, and this is, I'll come back after. This is because we had, after the cesium, we have achieved a lot of other transitions that are good clock transitions. A good clock transition, of course, for atomic transitions, we have tons of them. But not all of them are good clock transitions. A good clock transition is one that you can characterize well. It's not sensitive to environmental effects. And the excited state of this transition can take longer, so you can have more time to interrogate. So it's not like an optical transition of cesium, for example, is not a good optical transition, but because it takes roughly 13 nanoseconds of lifetime, and so you don't have so much time to interrogate it. But you can find in other atoms, like even in the fundamental state of rubidium, and other hyperpolarizability transitions of other atoms, like in optical transitions. So you can have a very thin resonance observed, like 1 millihertz, because you take 1 second of lifetime in strontium, for example, and then you have a lot of time to interrogate. 1 second is already a lot of time to interrogate. With this, you have a bunch of other atoms and other methods to interrogate. Of course, each transition gives place to a particular reference and a particular frequency. For example, for rubidium, it's not around 9 gigahertz. It's around slightly less than 7 gigahertz. It's 6.8. And for strontium, is in the optical domain, so it's 10 to 14 hertz. So you have all these frequencies, but as Kleppner said too, citing Teddy Hensch, you can nowadays link coherently all these domains, all these different frequencies with a frequency comb. So you can have even radio frequency or microwave clocks linked to optical clocks coherently. And this is what we had in other experiments, like Milson is going to talk about tomorrow. With ion traps, we have also neutral atoms with optical transitions. And this is the current, let's say, map of a fractional uncertainty. This is uncertainty, not stability. But this is the uncertainty for optical clocks here, arriving in 10 to minus 19 of uncertainty in 2025. Okay, and of course, this is a graph showing the slope of improvement of microwave clocks, and the fast improvement of optical clocks, and then another kind of a slope, it's like almost stabilizing the improvements in the uncertainty of optical clocks. But something that is very interesting in this graph is this region here, the green points here. The green points are the comparisons between optical clocks with cesium, cesium representing the microwave domain. What is the meaning of this here is because, like in these years here, the translation of the optical uncertainty to the microwave or radio frequency domain was not so good. So to use optical frequencies for GPS, for example, or for the international time, for example, was not so reliable because the translation from the optical domain to the radio frequency domain was not so good. And this is the point here, is that is more, nowadays, you have more reliable ways with frequency comms to transfer all the stability we have in the optical domain to the radio frequency use, even if it's much more that you need, let's say. Sometimes for GPS, maybe you don't need micrometer resolution, you know. That's much more about this. And this is something that we can see here in the last, in a recent paper from Noel Dinmark, talking about the roadmap towards the redefinition of the second, about the application opportunities of such higher or such lower, in fact, uncertainties, like 10 to minus 11. He's talking about geodynamics, geoid variation, because it varies with sea level and moon proximity and such kind of things. And other types or other kinds of fundamental measurements that we can test. This is not for, let's say, daily and spread applications, but are more for basic research and nowadays, of course. And these are the last results that we can have with atomic systems, but in optical domain. And the first one is with neutral atoms. That's 8 to 10 to the minus 19 with Junier group. And the other one is the single ion clock, but is the aluminum ion clock. That's a bit complicated sympathetic cooling with beryllium, and then you cool down aluminum ion and so on. But they could find 10 to minus 19 of systematic uncertainty. This is the estimated uncertainty of the measurement, taking into account all that effects that I told you before, the systematic effects. This is not about the stability. The stability that is given to them is this, 10 to minus 17 second to second, and 10 to minus 16 second to second. Of course, you take hours and hours averaging these to reach such kind of resolution and to, I would say, infer these high resolution measurements about uncertainty. So that's, that part of the talk was much more just to interpret these two numbers here, okay? And then this is nowadays the status of these last measurements. Of course, we keep going with these one that are the contributions of the universal time coordinate with all the countries that are contributing with the international time. And all them, the red ones are just receiving signal, comparing with local clocks, and providing the files with the comparisons to BIPM. And the green ones are the two-way communication systems that are better for remote comparisons. But these are the countries, or not the countries, but the laboratories that contribute with UTC. This is the map that's not changed, has not changed since 2018. Okay. Well, I hope that I could give you some brief view about the status of this nowadays, that started with not with Hubby interrogation method. It was the seed of the microwave clocks, to simplify. But then Ramsey gave us this insight of having the separated oscillatory field, improved a lot. It remained for decades. And then now we have this last result here. Oops. Very reliable. And this is still with a single pulse. This is, I would say that this still have some room of improvement if we could take longer, but because this is still with a single pulse of laser and not waiting so much and taking not so all the advantage of improving the stability. Of course, there are some more limits for the stability in the systems in this resonance here. But they are very outstanding and awesome results that they had already. So with this, I finish here, and I thank you all.
Thank you, Daniel. Is there a question? I have one. I know that for atomic standards, one usual topic is investigation of variation of fundamental constants. Do you have a plan on that direction here, or this is not in the roadmap?
No, not here. At least with our stability nowadays, we don't have this in view. Of course, you could have there are some very interesting results with alpha constant with fountains, but it's about limits of variation of the alpha constant, taking over years of measurements. But this is already done after, I think, 10 years, if I think with a SIFT observatory.
Okay, thanks. Further questions? No, yes.
Daniel, speaking about time and frequency basis and connecting with modern quantum technology, how does the precise clocks and everything fits into sensors, communication, computation, and so on? You know, I think we're going to have something tomorrow about measuring gravity, right? But because you see, we're going to have sensors, but we're going to have clocks together. And today the clock needs to be in a big container. Are we thinking about going to, you know, like compact clocks and things like this?
Yeah. Well, what I normally say that in a clock you have to get rid of all the environmental effects. In a sensor, different from a timing sensor, that's the clock, but it's another kind of sensor, you have to potentialize the effect that you want to observe. So let's say if I want to observe magnetic field, I go to another transition that's more sensitive to magnetic field. I'm not going to the clock transition that I operate in the system. But in a gravimeter and in a magnetometer, an atomic magnetometer, you go to another transition that will be disturbed much more by the quantity that you want to observe, like gravity or magnetic field or electric field, for example. So that I mean, it's kind of the same principle of observation. You want, of course, you can improve even the observation, but it's a clock made for this. Yeah. It's similar hardware, let's say.
Okay, I don't see further questions. So Daniel, thank you again, and that's it for today. We meet tomorrow. Thank you very much.